Homework number 6, problem 2 says repeat problem 1 for a temperature of 60 degrees C, assuming the given parameters were found at 20 and that the cable is copper. So from what we learned in chapter 4, we saw that the resistance of a conductor is temperature dependent. And so what problem number 2 is asking us to do is recalculate what the sending end voltage will be when the resistance changes. We should see that because the temperature is increasing, the distributed parameter for resistance that we previously had should go up. And so we were given a formula for calculating a change in resistance due to a change in temperature. That is, the new resistance at the new temperature is equal to the resistance at the initial temperature times 1 plus alpha times the temperature difference, which is calculated as the new temperature of the transmission line minus the old temperature of the transmission line. And so this will calculate, we can just throw R prime on there, it works for distributed parameters as well. So the only things we need to know are what the old resistance was, and then we need to know alpha here, which is the temperature coefficient of resistance. Now this is material dependent, so we have to look that up specifically for copper in a table. You look that up, we found in the textbook it's 0.004 per degree Celsius. And so that's the temperature coefficient of resistance alpha right there. So we can recalculate our distributed resistance parameter here. That is going to be R new prime is equal to 0.00893 times 1 plus 0.004 times the temperature change. We were initially at a 60 degrees, or I'm sorry, at a 20. Now we're going to 60. When you look up your temperature coefficients of resistance, make sure they match the units that your temperature change in is. So you do that multiplication, you should get a new R prime equal to 0.010359 ohms per kilometer. Hopefully that's larger since the temperature went up. So looks about right. So that's all that changed from problem 1 to problem 2. So what we need to do now is just go ahead and redo our voltage calculation. So remember, the voltage for the short transmission line is just the the receiving end voltage, 66.4 e to the third angle 0 degrees volts. Then we need to add to that the voltage drop across the line, which is the product of series current, 88.96 angle negative 30 degrees amps, and then the series impedance. So this is going to change. This is going to be the 0.010359 ohms per kilometer. The inductance didn't change. It's going to be J2 pi times 60 times 1.55 e to the minus 3, and then I need to multiply by line length, which was 50 kilometers. And so the sending end voltage for this new one is 67.75 angle 1.85 kV line to neutral, which if I put that on a line basis is 117.34 kV line to line.